Hi everyone, welcome to the algorithm seminar. Today we're happy to have Piotr to give a talk here. He's a professor at the Institute of Informatics, University of Warsaw, where he received his habilitation in 2009, and where he received a doctorate in computer science in 2005. His research interest focuses on practical application of algorithms, ranging from economic applications through learning data structures to parallel algorithms for data science. In 2009, Piotr Sankowski received also a doctorate in physics in the field of solid-state theory at the Polish Academy of Sciences. In 2010, he received the ERC Starting Independent Researcher Grant. In 2015, ERC Proof of Concept Grant. And in 2017, ERC Consolidator Grant. He's a president of IDEAS and CPR, a research and development center operating in the field of artificial intelligence and digital economy. He's also a co-founder of the spin-off company MIM Solutions. Please welcome our speaker.
Thank you. Yeah. So
maybe logistically, if you're better if you sit there because there's no camera here.
Okay. So I wanted to talk about the paper, like improved feature importance computation for tree models based on Banzhaf values. So this is the team that worked on the paper. So there are people coming from University of Warsaw, IDEAS, and actually the company Solutions. What kind of is the topic or kind of the problem we want to consider? So something which was kind of developed some years ago and is being used in the context of explaining tree models, and as well other kind of machine learning models are Shapley values, or which are kind of called SHAP or tree SHAP. And essentially, the idea behind all this feature importance measures is to kind of give some explanation or intuition why some features in the machine learning model are important or are not, or less important. So you can see here kind of an example. So you could have a kind of black box model that takes into some features like age, sex, BMI or BP, and outputs some prediction like 0.4. And essentially what you want to do, you want to split this output, like this 0.4, and attribute kind of split the value of the output to the features, like it's given on the right hand side on here. Yeah, so essentially you would say that age contributes 0.4 positive to the output, whether sex contributes negatively 0.3, and then the other two things contribute 0.1 to the feature. So, and essentially kind of what was done in this Lundberg et al. Paper in 2019 and 2020, they proposed something which is kind of interesting from the algorithmic point of view. So they proposed this tree SHAP algorithm, and essentially this is an exact algorithm that computes Shapley value-based explanation for tree models in polynomial time. Yeah, so this algorithm runs in time, which is TLD squared. So if you plus n, which is the number of features, and essentially, if you would give it one tree, then the complexity of the algorithm on one tree is number of leaves times the depth squared. So, and essentially, I mean, if you start using this tree models in practice, I mean, you at the end are computing a lot of tree explanations, and this is not that fast. So also finding the trees and using them is quite efficient. Then this explanations of computing them, finding them, take some time. So we ask the question, kind of, is this the best way to compute the kind of explanation for trees, and we started playing with Shapley values and kind of explored different concepts as well. And what we kind of find out is that it seems there are kind of better ways, or kind of better algorithm, or better kind of definitions of feature importance than Shapley values. And what we kind of, the main result of the paper is kind of reasons why, for example, Banzhaf values should be preferred than Shapley values. So Banzhaf values is, I will explain in a while what are the definition, how they differ, and what is the idea behind all of this, like these two concepts. But essentially, these two concepts in economy are competing and essentially are considered to be equal. So people say that, for example, I mean, these two concepts, Banzhaf and Shapley value, come from voting games or other kind of games, and for example, are defined in a context of voting games as a power of a kind of player in a voting game. And essentially, kind of economic literature doesn't really say which one is better for some reason. So there is no strict preference for this, and we show essentially that this holds here as well in the context of three explanations. But kind of the advantage, I mean, but besides of kind of conceptually which is better or not, Banzhaf values have some noticeable advantages over Shapley values. So first of all, they can be computed way faster than Shapley values. And I think second point is quite important. They are numerically stable, or kind of stabler. So Shapley values are kind of very badly, or maybe not directly Shapley values, but many algorithms for computing Shapley values, including the fast ones, are not numerically stable. Essentially, they do subtractions and many different things. And essentially, in many cases, you get random outputs out of these algorithms, and I will show some examples.
This what you showed us on the previous slide, was it Shapley?
Yes, so I mean, this is just a picture, no? So this is Shapley. I will give some more details of what we kind of show. And experimentally, kind of essentially, like Banzhaf and Shapley value give very similar explanations. So global feature importance is essentially the same. So there are very little differences.
In terms of ranking, or
in terms of ranking, L1 norms, L2 norms, whatsoever you would be looking, even the Kiley kind of ordering are very similar. So essentially, experimentally, there is no strict preferences between both of them. They essentially give the same explanation. And even for individual predictions, these things are very similar. But kind of the problem is that for individual predictions, Shapley values, at least some, like this fast implementations of Shapley values, make numerical mistakes, and which actually can dominate the output. So in a sense, kind of from meta level, game theory level, I mean, there are different kind of concepts or explanation concepts similar to Shapley values and Banzhaf values, and essentially there is ongoing discussion in this kind of from this perspective, or which definition to use, which kind of value to use. So, and some of them are better in different contexts, and some other are not. And essentially, you know, there is tons of things that other things that can be done. So what I will be talking about is these three things. So I will give you some more kind of insight on how to define these values in cooperative game theory, how to define Banzhaf and Shapley values. I will give a bit of an explanation of our algorithm for Banzhaf value and for versus the tree-shap value. And I will give you some more experimental kind of results and bit of theoretical reasons why one should prefer Banzhaf value over Shapley value, at least in the context of trees. So what is kind of where do this concept of Shapley value come from? So essentially, it comes from coalitional games. And in coalitional games, you are given a set of agents, say A1, A2, and A3, and this players can make some coalitions. Yeah, so they play some game, and essentially each of them can say, I play the game or not, and depending who plays, they gain some money. So essentially, there is an payoff in the game, but the payoff is for everybody.
Mhm.
Yeah, so everybody gains something.
Is it uniform?
No, so it can be arbitrarily defined, like here. Yeah, so each subset, so if some subset of players decides to play the game, then depending on the subset playing, all the players get some money, but they get the money together.
So it's so each player decides on a single bit of
Yes.
whether they play or not, and then there's a single group of players playing, and then do all the players get the payoff, or only the ones?
I mean, they, like the ones that play get the payoff, but they get the payoff together for the coalition.
Yeah, I see. So it's like split.
Yeah, so the question is how they should split the payoff between one another so that it's fair and so on. Yeah, so this is exactly the question, or kind of the Shapley value is the solution to
I see, because like their contribution to the payoff may be different, right?
yes, exactly. Yeah, so maybe some of them kind of are stronger in a sense and should get more money, and we should encourage them to play the game by giving them more money. Of course, I mean, so there are kind of two, essentially, like the game or kind of the concept or what we are considering. We should come up with a payoff function of the grand coalition in a way that the payoff corresponds to player contribution to the game. Yeah, so this is from game-theoretic side. This is a kind of Shapley value, or the concept is coming. Whether on the explainability side, essentially, kind of you should think of it as players being features. Yeah, so essentially you have some features present in the problem, or values, even values of the features, and they contribute to the output, and there is just single output. Yes, and what you want to do, you want to share this output between the features. Yeah, to say that the most important feature got the most kind of the biggest contribution to the output of your model. I mean, how exactly one defines this function, the payoff function, in the context of explainability is, there are different ways you could do it. I mean, I will talk about one of them. Yeah, so I mean, we want to divide the payoff of the grand coalition in a way that corresponds to the player contribution to the game. Yeah, so how to measure the contribution? Something which is typically used is this marginal contribution. So the marginal contribution is this. So it's defined in this way. Yeah, so you have a coalition, and you want to find or to define what is the marginal contribution of a player AI to this coalition. Yeah, so the marginal contribution is the difference between the value of a coalition with this player minus the value of the coalition without this player. Yeah. So kind of Shapley and Banzhaf value are kind of defined around this concept that we want to consider marginal contribution of a player to all coalitions in a game. Yeah, so this is like down there on my slide. You have one of the possible definition of the Shapley value. So it's Shapley value of a player I is a sum over all possible coalitions without a player AI of the marginal contribution of a player to this coalition, and it's weighted according to this kind of weighting function. Yeah, so it's it depends on the coalition size, and maybe not. Let me not go into the details of this kind of.
Is that
thing.
almost the inverse of A choose C, a denote of A choose C?
Yeah. Essentially, I mean, it's number of orderings, and I will go into more details what this weighting function means in a second. But let's just skip it for a while. But as well, kind of Shapley value is, and this was kind of one of the papers, like seminal papers of Shapley, is that he observed that actually this is the only way to divide the contributions that satisfies some axioms. So he defines the axioms which are symmetry. Yeah, so symmetry means that if two players always contribute the same to all coalitions, that they should get the same payoff. Then there is null player axiom. So if a player does not contribute anything to any coalition, it should get nothing. Additivity. So if you essentially add two games, yeah, so you have two payoff functions over the same kind of set of players, which are very different. You add them together, then the Shapley value of the like sum of these two games should add as well. Yeah, so this is additivity. And efficiency means that the total value of the grand coalition should be distributed among the players. Yeah, so you want to split the payoff between the players, so there should be no kind of leftover or whatsoever in the split. Yeah, so if you have this kind of seems natural kind of axioms, then there is just a single way you can define the split function, and this is exactly the Shapley value. So it's quite a natural concept in game theory. Yeah. But there are many different possible divisions. I don't want to really go at this moment into this, but a different kind of way of how to think about Shapley value is this one. Yes, so actually it's as follows. Yes, so you have a game, and you order essentially like players come into the game in different orders. Yeah, so you consider all permutations, like all permutations of the set of players. You order them in every possible way. Then they go into the game, and each time you consider the marginal contribution of a player in this order. Yeah, so essentially, yes, these players already entered the game. Now AI enters the game, and you consider his marginal contribution to the game. Yeah, so essentially this weighting function, weight function we had in the definition comes from the fact that you actually did not look on the order of players. Yeah, so you were considering him coming at some moment of the game, and then you in this order. Yeah, so so the Shapley value here is something. And there is a different kind of value. I mean, like in these voting games or whatsoever, there are kind of different things considered, and a different kind of way to share the payoff is Banzhaf value. Yeah, so the definition of the Banzhaf value is this. So essentially, now you don't. I mean, essentially, you look over all possible coalitions, but now the weight does not depend on the coalition size. You just sum it up. So you take average marginal contribution of a player to a coalition. So this is a Banzhaf value. I mean, Banzhaf value by definition is not efficient. Yeah, so it does not split the payoff between the players. It does not need to sum up to 1. But I mean, of course, you could. I mean, this is something we like because, I mean, in explanation of the model, we would like to attribute the output of the model to the features, to split the output on the model to assign to features exactly. and have no outcome. But I mean, essentially, you can simply normalize the Banzhaf value, so it's efficient. And there are very similar. I mean, there are tons of papers about different axiomatic definition of these things, and there are different axioms, and these two things are very similar. They can be defined in such a way that normalized Banzhaf value and Shapley value differ by one axiom, which is kind of similar but different. But in a sense, these two things are very similar. But somehow, I think the important thing was this story. Yeah. So essentially, Shapley value is an average marginal contribution of a player when they enter the game in this order, according to the permutation. Yeah, so somehow in Shapley value we assume that the order of players matter. Yeah. And in Banzhaf, we essentially are not really looking on the order of players. And this is something from the point of view of explainability of machine learning models, this is something which is non-intuitive. So essentially, it's unclear why the order of features should matter in the machine learning models. Yeah. So essentially, somehow, and what people say from kind of game theoretic perspective, and when you go through the papers that study Shapley and Banzhaf value and compare them to one another, essentially they say that they recommend, or these papers say give such a recommendation that when you don't know which of these two values choose, I mean, you should choose Shapley value when the order of of voting matters, or the order of players in the game matters, and you should choose Shapley value. If it doesn't, you should use Banzhaf value.
So one question. So for Shapley value, you're averaging over randomized ordering, right? So
Yes, exactly.
ordering, I mean, the average number doesn't seem to actually care that much about ordering, or what do you like?
I mean, of course, like here, like when you consider the machine learning models, order doesn't matter. Yeah, but there are voting games where order matters. Yeah, so if you can even define some artificial games when you can when you get tons of power when you vote after some other player, for example. I mean, and then essentially, if you would consider Banzhaf value, it wouldn't really correspond to what is happening. Whether in Shapley value, it somehow should count, but it's just an intuition. So it's more kind of a gut feeling that really a strict thing. Essentially both things work very similarly.
Mhm.
It's just, you know.
Or is it true that when the order doesn't matter,
Mhm.
these two values are similar?
They are.
Anyway,
There is no. I mean, in general they are similar, but I mean, if you consider specific games, that the values are slightly different. Mhm. So it's not that they are the same. Yeah. So if you consider concrete games, then these two things are different. So it's nothing formal I'm saying right now. It's just a takeout message or kind of gut feeling of the guys from economy that, you know, when the order matters, Shapley value is somehow better, but when the order does not matter, Banzhaf value is slightly better. Still, you know, I mean, when you look on the definitions, so another definition of the Shapley value would be, and this is kind of explains the weighting function. So if you sum up over all kind of permutations, not the subset, but permutations, then essentially this is averaging marginal contribution of a player over all permutations. And Banzhaf value is averaging marginal contribution of a player over every coalition. Yeah, but I mean, this kind of equations are exponential. Yeah, so you need to consider either all permutation or all subsets. Yeah, so it doesn't seem to be a clean way of computing it, but what the Slumberg paper showed is that you can compute it in polynomial time for trees, for decision trees. And what we did, I mean, we first of all shown an optimal algorithm for Banzhaf value. So essentially, the complexity of the algorithm for a tree is proportional to the size of the tree. Yeah, so number of leaves in this decision tree is proportional to the size of the tree. And kind of using similar ideas, we were able to improve the algorithm for computing Shapley values as well. What is somehow intuition between how they came up with the algorithm for computing tree shot. So essentially, it uses dynamic programming, and it starts from the root and goes down to the leaves, extending the size of the subproblems. Yeah, so essentially, in each move, it updates the state of up to d values. Yeah. And the update is related to the coefficient in the Shapley value and of its subproblem. Yeah, so essentially, they have d values because, like in each subset, the size of the, I mean, how to explain it well? So in the Shapley value, you need to have d values because for each of the size of the coalition, because I mean, if you go down the trees, then you essentially have some features or not, and present, and then essentially you need to have d values because this coefficient c might be different. Yeah, so either the size. I'm not sure I'm explaining it in the understandable way.
Is it true that once you look at the subtree and value a feature whichever defines your subtree, you can actually compute information so that for the entire feature you get in the bottom?
I mean, it's more complicated. I mean, essentially, like they get, so 1D is coming from the fact that you need to keep d values because for each coalition size, you need to have a separate value in the dynamic programming because kind of the weighting function is different for each coalition size. And then what they do in the algorithm, they essentially go down and update this value d times. And essentially they go, I mean, it's really hard to explain what happens in the algorithm, and I don't really want to do it. What I want to say is that where kind of comes because I mean it's really not an obvious algorithm, and how to say, it's not an obvious algorithm, and it's I would need much more time to explain it. Essentially, they kind of compute the contribution of the features, and then they go up the 3D times to compute the marginal contribution of each feature. And what they get is the complexity, which is TLD squared. To explain the algorithm, I would really need to define the dynamic programming and so on. It's really not straightforward. So kind of the improvement of the running time in our algorithms, first of all, come from the fact that the Banzhaf value are not weighted according to this function. So we don't need to store the different values while going down the tree in just one. So this is one kind of improvement. So one improvement comes from the definition of the Banzhaf value. And then kind of we find a way, kind of a clever way of actually grouping up the updates and doing the backtracking, which they did. So to compute the marginal contribution for each feature, they went d times up the tree, and we find a way how to do it essentially on average once. Yeah, because I mean this is kind of again the standard trick that like the Eulerian tour of the tree, essentially. Yeah, so instead of going to each of the subtrees, we can find the marginal contribution on average by going once around the tree. So the last trick improved the tree-shap algorithm from kind of TLD squared to TLD. As I said, I don't really want to go into the details of the algorithms. You can look up the paper. I mean, it's not, I would say it's nothing smart. It's really very tedious look on the dynamic programming than smart algorithmic things. You know? I think more interesting part is kind of experiments and how these things run in practice. So what we did, I mean, we did our experiments on two implementation of decision trees. So one was coming from sklearn, so this is called decision trees, and the other one is coming from XGBoost. So these are gradient boosting decision trees. And we looked on 4 data sets, which differ by kind of complexity and the number of rows, features, and so on. So Boston is like probably you seen this many times. So this is prediction of the price of house in Boston, Massachusetts. It's a very small data set. Then and Haynes is kind of health insurance data sets. No, this is not. This is socioeconomic status of people residing in US, and then health insurance is kind of the you need to predict who would be interested in health insurance, and the biggest data sets we use it's flights, and it essentially aims to predict the delays of flights. And we used some very kind of standard parameters for kind of running or generating the trees. We did not tune it. I mean, these are kind of standard parameters and so on. And what we can see. So we considered. I mean, these are kind of experiments related to the running time of implementation of tree-shap. So this is Lundberg implementation of tree-shap, and Banzhaf, this is our implementation of Banzhaf values. And essentially, like Banzhaf values are visibly faster. So on like the smallest data sets, essentially it's as small that you don't see any difference, but already on this bigger ones, there are considerable differences. So, for example, for this sklearn decision trees in this health insurance, I mean, you either instead of running the algorithm for half an hour, you get the answer in 5 minutes. And in flight data sets, the difference is actually quite huge in both kind of examples. So, what you need to keep in mind that gradient boosting trees are essentially generating many trees which are very shallow, whereas this sklearn generates less trees which can be way deeper. And this is where kind of the difference comes from, because the Shapley value has this the depth squared complexity. So essentially, you get like considerable time savings for the gradient boosting decision trees and even more for this skyline decision trees. So the next kind of experiment we did is we computed something which is called global impact. So global impact is essentially the impact of the feature averaged or summed up over all examples, like all kind of rows in your data set. Yeah, so you want to consider essentially over all kind of decisions the algorithm made, what is the contribution of the feature to each decision. Yeah, so you take this Shapley value and Banzhaf value, absolute value of those, because they could be negative for a given decision, and you sum up the absolute value over all kind of rows in your data set. And essentially what happens in all these data sets, like all 4 data sets, or and both algorithms generating this decision tree. So it does not hold for all kind of data sets, and I will go in a second. So it holds for 3 data sets, like the smaller ones. Yeah, so essentially these orderings are indistinguishable, and even the values assigned to each features are almost the same. Yeah, so this is an example. So essentially Shapley and Banzhaf gives you almost the same. Yeah, so no visible differences. However, kind of in the flights data set, which is the biggest one, like in the first most important features, I mean that there are very small differences, like here, like which on the things which already have very small values. Yeah, we looked as well on the Cayley distance. So essentially we looked on the top kind of features returned by the model and looked how many changes you need to do to go from one permutation to the other one. So essentially Cayley distance is the number of swaps that are needed to go from one permutation to another one. Yeah. So if you have these 2 examples, then essentially you look on the permutations, and the number of permutation is the distance between these 2. The number of swaps is the distance between the 2 permutations. Yeah? So the 2 permutations have Cayley distance equal to 3. So if some features are missing, then they are added at the end of the permutations. And essentially, like if you look on the top 3 features, then essentially very few differences can be seen. If you look on the 10 features, then again, essentially it's a kind of 1 to 1 or less than 1 swaps, or here for decision tree the differences are bigger, but essentially the number of swaps is very small between these 2 permutations.
So these numbers, because number of swaps is integer, right? So these are scale.
Average numbers of swaps between the permutations. Yes, so we look on each kind of each row, so each kind of instance where you do a prediction. Yeah, for this prediction, you compute the most important features. You order them by importance and consider the order.
Okay.
Yeah, so essentially it means that these things are very similar. Yeah, so you see the same top 10 features. Like if this is 3, then essentially like 7 features certainly agree between one another. Yes? So it's very similar.
So a swap can change 2 features, right?
Yes.
Wondering like what's a random, if we get a random ordering, what's the Cayley distance between?
I think we would need to compute it, but I guess it's log n, no? Like it's n log n, for like if you have 10, then it will be. No?
It's
like sort
Smaller than
I think
M.
I think it would be close to n because you can
close to n.
sort any sequence in n swaps.
Probably
N minus
order of
one,
n.
definitely smaller than that.
N minus one, yeah.
Yeah, it's probably order of n.
Probably, okay.
But if it's like N over 2, then
Mhm.
it's a big number, actually.
Yeah, because I mean, yeah.
I mean, we consider it as well, kind of the mean average error and root mean square error, whatever, and
It will be order of n in expectation.
to be ordered.
But the constant matters here. Like,
That's true. Like I guess n over 2, but yeah, that's also correct.
So here it's like in the right chart, it seems that the number of like the
Oh, that's
distance
already
is higher.
over.
I guess this makes sense because the depth is higher, right?
Exactly.
So I guess as the depth increases, the two
Yes, and-
algorithms become more different.
But we think that the reason for why this is that different, actually, more different than expected, is due to the problem with the Shapley value. And we looked on it. I will give you some more kind of examples, but like for something which we proved for Banzhaf value, I mean, it's kind of very pessimistic, weak, and so on, but at least you can prove it. So you can say that if the tree depth is d, and epsilon is kind of the arithmetic error of your machine, then the Banzhaf values can be computed with this error. Yeah, so essentially, if the depth of the tree is smaller than the inverse of your kind of arithmetic errors, then it should be quite fine. Whether for tree shop, you cannot prove anything like this because tree shop makes subtractions. Yeah, so I mean, you can come up with a slower impractical algorithm for tree shop that avoids subtractions, and then it behaves very similarly to Banzhaf value. But essentially, like in this test, this part and kind of the growing differences for DT comes from the fact that the Shapley values start to make mistakes, numerical mistakes. And this thing can be quite big. So first thing we did, I mean, we came up with kind of a synthetic example, synthetic tree, when we kind of know the Shapley and Banzhaf value explicitly. And then we ran the algorithm, and what you can see is that the error of the Banzhaf value essentially is constant. It's not growing. It's very slowly increasing with the depth of the tree. Whereas the error of the Shapley value increases quite high, quite fast, meaning that for depth around 60, it can dominate your output because it's around 10 even. Yeah, so it can, if your kind of model prediction is 1, then essentially the numerical mistakes can dominate your output. And for the DT model, on some of the data sets like flights, we had trees which are kind of depth 40 or 50. Yeah, so you can already kind of suspect that bad things can happen, and actually they happen. Yeah, so for example, we even looked on 2 implementations of the Shapley value, and they kind of gave totally different results, even like totally absurd numbers and things like this. Yeah, so it really does matter, and is quite problematic.
I wonder if this absurd number is coming from computing these factorials exactly, which could be like very small numbers.
No, so factorials are not small numbers, but the problem is that somehow you are subtracting small numbers in the computation. So you can, as I said, I mean, we can come up, we have an implementation of a Shapley value which does not use subtractions, and then it works well. It essentially does not make numerical mistakes. You can prove the same statements, and then this thing wouldn't happen.
But it's slower.
But it's slower. Right?
Is it the one on the left, or
no, it's slower by another factor of d. So it's really inefficient. So I think it has the cube or something like this. So it's really not useful in practice. Whether what I was saying, whether these mistakes don't really come from the fact that there are factorials. I mean, they come from the fact that the algorithm uses abstractions.
And if you compare this exact algorithm, which is slower, with the like Banzhaf, is the difference like very small in the?
It's very small, so it essentially becomes almost the same.
Okay.
Yeah, so the differences decreases, and there are some differences, but essentially for this part like DT, you are getting something similar to what you are getting here. Yeah, because this gradient boosting decision trees, they are essentially of depth 8, 10, something like very small constant, even for big trees. So this numerical mistakes don't really matter that much. Yeah. So kind of the takeaway message is first of all the Banzhaf value can be computed noticeably faster than the Shapley value. There are probably, it should be probably and not probably. More numerically stable, and essentially kind of they deliver the same global impact. So for global impact there were no visible differences, and for individual predictions, when you look on kind of each prediction for a given kind of row, even individuals, and this explanation are quite close and very often are almost the same. And essentially kind of, as I said, I mean, one should not stick to one concept, and maybe depending on the context, look on different ones and kind of try to use something else which might be better suited than Shapley values. Thank you. Questions?
What is interesting to look at? Nice, given your result.
I think
You did all smart things and
no. So I wouldn't say we did all smart things. Something which we think should be possible but cannot do it is actually to extend this to some more complicated kind of decision models. So that you can consider decision trees, but for example, there are decision graphs which are more powerful. And we expect that for more complicated kind of, I mean, decision graphs are not as powerful, of course, as kind of, or could be seen as something maybe slightly similar to neural network, but they are not. But essentially, we think that for decision graphs, you can prove approximation algorithm. Also, there are hardness algorithm, like hardness results. So for trees, you can compute these things in polynomial time. For more complicated kind of decision models, there are proofs that these are, for example, hash P complete. But what we think and what we try to do, but I don't know how to do it, is to get some approximation algorithm.
okay, so there are none.
There are none. For this harder decision model, there are no such results. They are kind of exponential. You can prove exponential.
If you want exact algorithm.
Yes, time algorithms are exponential, approximation algorithm, whatever you want. But we believe that for some of the stuff, there should exist polynomial time approximation algorithm, even approximation schemes. Because these things are very similar, or kind of the reduction, hardness reduction that are being used go through the network reliability problem. And for network reliability, you have efficient approximation schemes.
Okay.
So this is one of the things. And there are other things because, for example, you might have different definitions of the I did not go into details there, but I mean, I skipped this part, but kind of the feature importance is for tree. I mean, there are different possibilities how you could define it, and for some of them there are polynomial algorithms. For other ones, that there are not.
You mean different than these two that you mentioned, Shapley and Bell?
Mhm.
Okay, thanks.
And of course, one could consider different features like this explanation. So we consider Banzhaf and Shapley, but I mean, if you would open a paper book, you would find 10 more, and people did not consider really looking for algorithms for computing them even on trees.
Hi, Piotr. Yeah, thanks for the nice talk. So both Shapley and Banzhaf values will tell us the importance of features in a model, right? Okay. So my question is, do you think say both of these values would be used for model explanation or model pruning? So which is the primary use case for these values?
I mean, they are typically used for model explanations, but I know that people try to use them for model pruning as well.
Mm-hmm.
But I mean, we did not do such experiments.
Mm-hmm.
But I think that they can be used for model pruning. I know people have been using them like this, and mhm.
Okay.
How is
thank
it
you.
different?
So explanation essentially is kind of it does not change your model. I mean, you're having a model, and essentially they are saying this feature contributes so much to your decision. Whether model pruning is changing your model to work with less features. So essentially, you are simplifying your model.
Yeah, I mean, I get that, but I'm just wondering, does this mean that like it's hard to think of a model pruning approach which is not pruning the least important features, right?
I think that like the least less clear thing is like maybe this gives you good attributions for a single example, but then once you average over many, like it's not clear whether this will.
Basically, correlations between features is what this is not capturing, right?
Yes. Yeah.
I see.
And model pruning usually works better. I mean, this is something we talked about when you do it iteratively. So essentially, you might have 10 correlated features, and essentially all of this attribution would say exactly the same value to those features.
So then if you had like a dynamic algorithm, you could in principle use it for pruning, right? When you start with the...
Yeah, thank you.
Let's thank the speaker again.
Thank you.